And in my today's session, I'm going to first discuss about the syllabus which you are going to follow in this semester. First of all, good morning to all of you, and I welcome the CSE Section A students to the first class of BSM 101. So first of all, I'm going to talk about the syllabus because to continue with the subject, you have to know the syllabus very well. But before that, I ask all of you to write your student IDs in the chat box, and that will count your attendance. So quickly take some time and write your student IDs in the chat box so that I can save it. That will count your attendance. And during the session, I must tell you that since I am using the trial version of Zoom, and because of that, I have 40 minutes time limit. After 40 minutes, the class will, the session will be disconnected automatically. And after that, you have to join by clicking the same link through which you have joined now. And the link which I've shared with you, this is my personal ID and password. So that will remain same always. And what you have to do is that you are supposed to click on the link on your scheduled timings of the class, and then you have to join. Okay, so 24 participants have written their student IDs in the chat box. Others, I think, are not listening to me because there are 30 participants. Others, please write your student IDs in the chat box. Otherwise, the attendance will not be counted. Okay, and taking attendance by the usual process, by calling out your names, that will just kill time. So please write your student IDs in the chat box so that I can save the chat to get your attendance. Okay, so you do it from your end, and let me start my today's session. Hope that you will be enjoying the session of BSM 101. First of all, I am going to talk about the syllabus. Now, you see, just a minute. Your subject code is BSM 101. BS stands for Basic Science, M stands for Mathematics, and this is the serial number of the subject. So BSM 101, 1 stands for the first semester, and 01 is the serial number. So this is your subject code. You have to keep in mind. And therefore, it is written here Basic Science course. Okay, so its course title is Mathematics IA. And this subject matter is only meant for CSE and IT students. Other non-CSE IT students, they will not be studying this course of mathematics. For them, we have BSM 102, and the subject code is also different. That is Mathematics IB. And the total credit for this particular subject matter is 4 credit course. Okay. And why am I telling all these things to you is because after 2.5 months, you are going to fill up your examination form in Macaut. And there, if you put the subject code as BSM 102, as one of the IT students, one of the seniors once did it, you will be in trouble. So be very careful when you put your subject code. Remember, this is a basic science course, so this BS is there. It is a mathematics course, so this M is there. And first semester course, so 1 is there, and 01 is the serial number. So in this way, you can remember it. Okay. Now, in this particular subject matter, in this particular course, there are in total 5 modules. Module 1 consists of calculus, where integrations will be discussed. Module 2 is having calculus in it with differentiation as the point of discussion. And in module 3, we have matrices. Module 4 and module 5 are totally based upon a new topic, which is called vector spaces. Now, I know that you know a little bit of calculus and differentiation and integration and matrix theory. You know a little bit of those things. from your school days, although in matrices we shall be learning the advanced version, not the old one, the advanced version. You can see the terms like in rank of a matrix and terms like linear independence. These are some advanced version. These are advanced topic of matrix theory. Calculus, you know a little bit, and this L'Hospital's rule, etc., etc. And integration, there are definite integrations and surface areas and volume of revolutions. So what I have decided for my today's session is to get you into the domain of module 4, which is vector space, because it is very new. Vector space is very new topic. 40 participants are there, I can see. So those who joined late, I asked them to write your student IDs in the chat box so that I can save the chat for your attendance. Please do so quickly. Those who have not written yet. Now, I have decided to discuss vector space, keeping in mind that vector space is a very important topic and it is a topic of linear algebra. And linear algebra is a topic which is very much useful in studying engineering, any stream of engineering. And you may think that since I am a teacher of mathematics, I'm telling these things, but you can verify the facts from various sources, because sources are available nowadays in the internet. And internet connection a little bit unstable today, so therefore it got disconnected. And okay, let me share the screen once more. Since it suddenly got disconnected, I suggest all of you to once again write your student IDs in the chat box, because otherwise just a minute, hold on. Can you see my can you see the screen I'm sharing? Okay, okay, fine. So let me continue. So what I was telling, that vector space is a very important topic, and it is a topic of linear algebra, and linear algebra is mostly used in engineering courses. And the application of this particular subject matter may not be understood by you right now because you are at the beginning stage, but later when you will be dealing with other different your core engineering topics, you will be able to see the applications of linear algebra over there. Okay, so that's why, since it is very new, I have decided to start with vector space and linear algebra. And thankfully, this matrix theory, which we have in the syllabus of BSM 101, this matrix theory is also connected to vector space. Okay, so I shall try to correlate at some point the matrix theory with the knowledge of the vector space. So for this, you have to wait a little bit. So with this brief introduction, I'm going to start my today's session formally with the discussion of vector space. Okay. I have prepared this note specifically for you, and where I'm going to talk about a term which is probably you are not familiar with. This term is called space. And obviously, since I'm going to talk about vector spaces, therefore you have to know what space is. Okay, so I'm going to talk about what space is first of all. And remember, students, one thing, that this particular subject that is called mathematics, and especially the subject you are learning, the linear algebra, it's a subject which requires a tremendous amount of patience. So if you are lacking the patience, then you will not enjoy this subject matter. And since this mathematics, we always call it philosophically that it's kind of language. So if you do not practice the language by doing problems and sums, the things will not be understood by you. So if you are lacking your patience, then try to increase it. Okay, so that you should enjoy, because it is this course is actually very necessary for your further um, that applications in engineering, which will be dealing in the coming days. Okay, so first of all, I'm going to talk about what space is. We all know that set is a collection of well-defined distinct objects. Okay, we all know that, and your set is a collection, and the collection has some elements in it, and that those elements must be well defined and they should be distinct. This definition is known to me. So I'm going to show you, first of all, two pictures where you can see that some students are sitting in the classroom. First picture shows that some students are sitting in the classroom taking notes from the teacher. The teacher is showing some things on the board, and you can very well say that this picture, we can call this particular scenario as a set of students. If I do not consider this person, if I exclude him from the picture, from the set, then I can consider this particular uh, uh, circumstances the collection of students, and all the students, their characteristics, their personal information, they are all distinct. And since we know that this collection is a collection of student, so this, and since we are uttering the word student, so it is well defined. So obviously I'm talking about a set. And if you talk about this teacher, and you say to me that we must not exclude him, then we can take him to a different set where he will only belong, and we will say that the teacher is actually uh, he belongs to a singleton set containing single element. But here my point of discussion is not about the teacher, because he is alone here. Here I'm talking about the students, because several students are sitting over here. So this is a collection, this is a set. Okay, and I'm going to show you in the second picture that there, you can imagine that in the evening, these students who are sitting in the morning in the classroom, they are going to the pub and disco to have some party with their friends. Okay, so these students are dancing over here. Okay, so we can call that we can say that this particular collection is a collection of students. Now in the pub or disco, not the students not only go, but other people are also there. I'm excluding those people from my from my study, and I'm only concerned about the students who were in the classroom in the morning, and now they are in the pub, uh, uh, in the disco, and having some party. So this is also a collection of students. Okay, so I'm considering the same set of students. First, they are in the classroom, and then in the evening, they are in the disco. But in both the cases, the collection which I'm talking about is a set. It's just a collection of well-defined distinct objects. Okay, these are not spaces until I set some rules for these particular collections. For example, you know that the rules defined, the rules by which the classroom is defined is actually not similar to the rules by which the discos are defined. Okay, so if suddenly, say for example, in the classroom we have to follow some protocols. Okay, I'm not talking about online classroom, because right now as I'm teaching you, and on the other side of the portal you are listening to me, I am pretty much sure that most of you, not all of you, are listening properly. Some of you are feeling sleepy, some of you are just online and not listening to anything. Some people are there who are listening very attentively. So I'm not, and this is beyond my control, so I cannot talk about I am not taking the reference of that particular system, but I'm taking the reference of the system where physical class is going on. And you know that the physical class is governed by the rule. What rules? Sudden, you in the physical class, you cannot cannot shout suddenly. In the physical class, you cannot start dancing. In the physical class, you cannot assault others. In the physical class, you cannot argue with the teacher. In the physical class, you have to be well dressed and well behaved. These are the rules which has been set by the authority. Okay, but if you violate the rules, then you get punished. Being in school or you be in college, the definition of punishment is different, but you are punished for violating the rules. Okay, so this classroom, this set is governed by some rules and you have to follow it. Similar is the case with this disco. Disco is also actually having some rules of its own. You cannot go there by wearing dhoti and kurta, or everybody will start laughing at you. And you cannot you cannot go there and start reading a mathematics book. People will think that you are mad. And you cannot go there and start fighting with another person. So the bouncers will throw you out of the disco. Okay, so this particular collection, this set, is also governed by some rules. Now, when the set is there, only set is there, we call it set. Okay, it's just a collection. But now my sets, my two sets, the set of students in the classroom and the set of students in the disco, they are individually, they are governed by some rules. And when a set is governed by some rules, such a set is called space. Okay, so a space is a collection where it's the collection of some elements where the elements are actually following certain rules. That collection, that type of collection, along with the rules, are called space. But when we talk about space, and if you utter this word space to a layman, he thinks about the universe. Okay, isn't it? So if you ask me that whether that space has any connection with this space, I must answer that yes, there is a connection. When a child looks into the sky and you tell him that, see, the stars are there and the planets are there, you give him a telescope and you teach him how to use that telescope to see the planets and asteroids. Then the child gets amazed and he say that it's a collection. Yeah, it's a collection of stars, or it's a collection of planets are there. It's a collection of there are some asteroids. I can take the collection of asteroids also. He only talks about collection. When he is in school, he comes to know the fact that that collection he is talking about, this collection is actually called set, because if you take the collection of stars, it is well defined and distinct. So it is a set. If you take the collection of asteroids, all asteroids, these are distinct from one another. So, and this is a collection of asteroids. So we can call this collection as a set. But when he goes to college, just like you have come to this college, now you have to know something else, something more about this collection. That this collection, the set of stars, is not just a collection. These stars are actually governed by some rules. The Einstein theory of relativity, or having some geometrical properties in it. Okay, so once you say that this is a collection of stars governed by some rules given by Einstein, I can call that collection as a space. So that space is actually a special case of this one, which I have defined just now. So what is space? Space is a collection of a set which has some predefined added structure. In mathematics, what happens, in all around us, we see various things happening, and the mathematicians try to give a universal structure for every situation which looks different. But when you keep those situations individually and keep it inside your defined structure, they look very same. So a classroom having some properties in it, a disco having some properties in it, and a space of a set of stars having some governed by some rules, actually mathematically they are all same because they are all spaces. Okay, And if you ask me a pure mathematical example for space, I must talk about field. What is field? Probably you have learned field in the school, in your school curriculum when you studied real number theory, but probably you have not studied it properly. Real numbers, we all know, stretching from minus infinity, the collection is stretching from minus infinity to plus infinity, open interval, containing infinitely many points. You can, if you consider the points only, rational points, irrational points, natural numbers, rational numbers, I mean integers, positive, negative, whatever, this is a collection. But when you say that, okay, I can add two numbers commute with each other with respect to addition, I mean a plus b equal to b plus a, we can take two numbers, we can add them and we can multiply by another real number, and which is called distributive property, a into b plus c. So is equal to a into b plus a into c. So when you are saying these things, that we can perform these operations on the set of real numbers, operation of addition and operation of multiplication, then that real number also, the set of real number also becomes space with respect to those operations. And this space has a special name which is called field. Okay. Your physical vectors also are governed by some rules. Okay, so we can consider those vectors inside a set governed by some rules, so they become space. So everything now looks same. Once you know the space, everything looks very similar to one another. You cannot distinguish them individually. They fall under the same umbrella. I'm not going to discuss in details about field, because field is actually a topic which is, if you want to go into the details of field, then it is a topic of abstract algebra. It is a separate topic, okay? But field is extremely necessary. Field is extremely necessary for our discussion of vector spaces. Okay, so that's why I have written the definition here, but I have not uh, uh, explicitly written the properties which will be followed by the field. Now, only real number set is not a field. Complex number set with complex number addition and multiplication, that set can also be considered as a field. But we mostly use the real number set because we basically deal with the real system. Okay, so, and it is also not that case when you talk about, when you go into the domain of quantum mechanics, the quantum mechanics you have to deal with, and there are various other engineering situations where you can deal with, we have to deal with the complex system. Okay, so complex number set with complex addition and complex multiplication, these are called, this is also a field. Real number set with real number addition and multiplication, they are also field. So with the knowledge of this field, let me go to the discussion of the vector space, which is actually the subject matter of our course curriculum. If you have any doubt, you will be able to you will be able to ask me in the third session. Okay, so just you hear, and if you have any doubt, you will ask me the third session, not now. Okay, I can see, say, a boy raised his hand, so you just wait and let me continue with the class, and then I'll answer your questions if you have any. So to define vector space, I have selected this picture. Now this picture, if you show this picture to a child, the child will say that, yeah, it is a picture of a car racing, and this picture has been taken from the famous animated movie called Cars. And this is a picture, just probably it is also from some animated movie, I don't know. I like this picture and it is very relevant to my topic, so that's why I had chosen it. And I have merged the two pictures together. Now I'm going to explain something to you, so you listen to me very carefully. Assume that these four people, these four guys, they are car racers, and now they are waiting for their turn to go into the field. They want to race the cars. Okay, they are quietly sitting, and everybody is thinking about who is going to win the race. Okay, so this is a collection of four persons, car racers. And when they go to the racing field, and they get their control on the will, they become aggressive. And now you look at their faces. Okay, you can look at their faces. So that is also the collection of these people, but they are racing now. What I can do when they're sitting quietly, I can consider these persons, 4 persons, I can name them as person 1, 2, 3, 4, and I can consider their masses to be M1, M2, M3, M4. And when they are in the racing field, controlling their wills, I can consider this person with respect to their velocity. And I consider the velocities v1, v2, v3, and v4. But you know that masses are scalar quantities and velocities are vector quantities. Masses have no directions, but velocities have directions. So these two sets are actually different sets. Okay, so set of mass is a set of actually scalars, and set of velocities are actually set of vectors. Okay, but they correspond to the same set of persons. Now, with respect to that, if I consider a set capital V, where I am considering the all possible velocities that we can consider, and I considered another set capital F, which is a set of masses, where I can consider all possible masses of the persons, then obviously you know that it is pretty obvious that this set V is actually a set of what? An infinite set, because it contains all possible velocities in it. And this set capital F is also an infinite set because it contains all possible masses in it. Okay, so therefore I have considered these without any loss of generality. I have considered this set V as infinite set and this set capital F as infinite set. Now what I'm going to do is that since these two sets are different, what I'm going to do, I'm going to connect the two sets together in some way. Okay, so let me show you the connection. So I'm thinking right now that what can we do with these particular sets, set of velocities and set of masses. Okay, so after a little thought, I have come to know, I have understood that, okay, if I have a set of set capital V, I can define some operations in it in the following manner, that I can add two velocities and to get a different velocity. So if I consider two elements from the set V, V1 and V2, then I can add them. This is my first operation which I have defined. And also, if I consider an element from the set F, say M1, and another element small v1 from the set V, I can multiply them, because when I multiply the velocity by the mass, you know that it becomes momentum, and momentum is also having some direction. And momentum is also, although I'm using the term momentum, you know it is actually a kind of velocity, because if you have mass, some mass, say m, so your velocity is getting increased by m times from your previous velocity. So m1 v1 is the m1 times velocity of v1. So it is also a kind of velocity, but we in physics we separately known it as momentum. So we can consider m1 v1 to be the member of my capital V. Okay, but after defining these two operations, this you know that it's operation of addition. But you have to know that I am not adding two masses together. I'm actually interested in adding two velocities together. So I'm actually adding two vectors. And here I am not multiplying two vectors together. I'm not multiplying two scalars together. I'm multiplying the scalar with a vector quantity. Okay, so I have specifically defined the operation in this manner. Okay, and therefore what I am doing, I can call this addition as vector addition, and that multiplication as scalar multiplication. Although I'm multiplying this as vector quantity by a scalar quantity, this multiplication is known as scalar multiplication, and this addition is called vector addition. After defining these two operations, what I'm going to do, I'm going to see with respect to these operations, what other properties these sets capital V and capital F satisfy. So I find the following properties which are being satisfied by the velocities and as well as by the masses attached to velocities. First of all, I have seen that if I add two velocities in this manner, v1 plus v2, it is same as v2 plus v1. So the addition of these vectors actually they commute with each other. So they are commutative. Okay, you can think that sir, it is pretty obvious that everything commutes. Everything commutes. So is this property extremely important? I must say yes, because if you give a little thought, you will identify that if we talk about matrix multiplication, two matrices of same order, okay, say for example, 2 by 2 matrices you are taking, AB is not always equal to BA. So always the things are not commuting with each other. If you take the set of integers, then 2 minus 1, and if your operation is minus minus, then 2 minus 1 is not same as 1 minus 2. So everything doesn't commute. So commutativity property is very important, although it looks very easy, okay, initially. Then I can take three velocities together and I can associate the velocities in the following manner. I can associate the two velocities together inside the bracket, and they're added. The addition, after addition, the velocity which I get, I can attach this velocity to v1, or I can contain the two velocities v1 and v2 together inside a bracket, and then I can attach this to the velocity v3. This property is called the associativity property. Okay, then you know that if your car has a breakdown, okay, and it has stopped for some reason or other, then the velocity is zero. It's called zero velocity. And a zero velocity, when added to any non-zero velocity, doesn't change the characteristics of the non-zero velocity. So I can write vi plus 0 equal to vi. This 0 is not the scalar 0. This 0 is the velocity 0. It is a vector 0. And if your car is moving in that direction and another car is moving in this direction with equal velocity, then I can say that your velocity is the negative of that velocity. Okay, so I can consider for each velocity, I can consider the negative velocity, so that when we add them together, I can get the zero velocity. Net velocity is zero. So in this way, with respect to vector addition, I have seen that this vectors satisfy certain properties. Okay, I have actually carefully taken this example because you are familiar with physics. I could have taken other examples, but I think you are not familiar with those examples. So I have taken an example which you are familiar with very much. So I'm talking about physics right now. What else we can do? So what I can see that, yeah, we have talked much about adding vectors. Now let's talk about multiplication of vectors by a scalar quantity. So what I can do is that it is pretty obvious that if I take a velocity vi and if I multiply this velocity by the unit mass, then obviously your velocity will not change. So this is a kind of operation which I can perform. Okay, unit mass when multiplied by the vector, scalar quantity, unit scalar quantity when multiplied by the vector doesn't change the vector. Very good. What else we can do? We can now connect. Oh, one more property is there. We can select two scalars, two masses together. Their product has been taken, and then this product has been we multiply their product by the velocity v1. It is same as if we first multiply v1 by one of the masses m2, and then the outcome, when we multiply v1 by m2, then this quantity m2 v1 is not a scalar quantity anymore. It becomes vector quantity. You already know, and we can multiply this vector quantity by the scalar, by the mass m1. So we can associate these with respect to multiplication in the following manner. And lastly, we can connect this multiplication operation, scalar multiplication operation, and addition operation together. So we can take two velocities, any two velocities. I am taking v2 and v4. Without any loss of generality, I can consider any two velocities. So v2, v4, they are getting added and getting multiplied by the mass m3. So we can write it as m3 v2 plus m3 v4. This is a vector quantity. Okay, this is a vector quantity because this is a vector and that is a vector. And also I can take two masses m3 plus m4, and I can add the two masses together. I can add the two masses together and I can multiply I can multiply the two masses, the quantity by the velocity v3, and in that case, I can write it as m3v3 plus m4v3, which is also a kind of vector. So how many operations have I performed? And after further getting into the details, I have seen that out of these operations, there are no other operations. All other operations can be converted into this. So you can also get, you can also think on this particular thing, on this particular point. So how many operations have I performed? I have performed 1, 2, 3, 4. 4 operations are there. And then I have performed this operation 5. And under 6, we have 3 operations actually. So 6, 7, 8. These 8 operations, they are actually the rules by which the physical set of vectors and scalars, they are actually satisfying. So if this is so, then my velocity v, the set v of velocity, the set of vectors, and the set f of masses is the set of scalars. And if we consider these operations, I'll say that this capital V, the set of velocities, is the vector space over the field capital F. We'll say this vector space V is the vector space over the field capital F. So initially, I told you in the beginning of the session that field, to learn vector space, field is important. So that's why you see how this field is connected to the vector space. Okay, field is also a kind of algebraic structure. It is also a kind of space. V is also a kind of algebraic structure. It is also a kind of space. The vector addition and scalar multiplication is different from the addition and multiplication of the elements of field. Sorry. So we can interconnect them. We can connect them together. So this was an example. Now I'm going to define mathematically, as I told you, that whatever set you consider, and if you put any rules on that, that becomes a space. So as I have got, with respect to my physical situation, as I have got the rules governed by the set of vectors and set of scalars, I do not want me to be confined in the domain of physical vectors only. So I started thinking, and I now decide, okay, let us define some rules, basic general rules, and let us find sets, collections which will satisfy the rules. Okay, because I don't want to look into the physical vectors separately. I always try to remember the rules, and whenever a situation comes to me, I will try to find out whether this situation are following the rules defined by me. And that rule is the definition of vector space, which I am going to read for you in this classroom right now. A vector space or linear space. Why is it called linear space? It has 2 reasons. Because it is you may say that it is a subject matter of linear algebra, therefore it is called linear space. No, it is not. It is called linear space because in vector space, when you will learn vector space, you will see that we will be dealing with linear equations mainly. So, suppose I give you an equation which represents a curve y equal to x squared. To study y equal to x squared is not that much easy, but when you consider a tangent at a certain point, you are drawing the tangent, you are seeing the movement of the curve. Okay, tangent gives me a feel of movement of the curve. So if this tangent, this particular portion, small portion where you draw on the tangent, this portion is actually linear, and you are actually converting a nonlinear system into a linear system. So it is very easy to study linear system than to study nonlinear system. So with respect to the knowledge of vector space, we shall be dealing with solving system of linear equation, and therefore sometimes vector space is called a linear space. So a vector space capital V, now this capital V is not my set of velocity. This capital V is any set. A vector space capital V over a field capital F consists of a set on which 2 operations called addition and scalar multiplication are defined, so that for each pair of elements small x, y in V, there is a unique element x plus y. This notation is plus notation. Consider this to be my plus notation. I am coming to explain why I have written this plus notation inside circle. You will understand. But first of all, this is plus and this is multiplication, dark dot. So you just carefully listen to me and I'm going to explain it to you later. So there is for each pair of element x comma y in V, there is a unique element x plus y in V. And for each element small a in F and each element x in V, there is a unique element a dark dot x, a dot x or ax in V, such that the following conditions hold. What are the conditions? Now you can see that whatever I have written above, I have just showed you, these are actually similar to that. That example actually is a special case of these operations. So first of all, I have written the properties, I have named the properties as VS1, VS2 to VS8. VS stands for vector space and 1 means the vector space property 1, vector space property 2, vector space property 3 and so on. And what is the first property? The commutativity of addition. So I've taken two vectors x and y and I'm writing x plus y equal to y plus x. Second was associativity of addition. So I'm taking three vectors x, y, z and I'm writing it as x plus y plus z is equal to x plus y plus z. Then you know, try to recall that I considered the zero velocity. So now I'm considering a zero vector, some zero vector. If it is a velocity, then it is zero velocity. Okay, then zero vector, I'm defining the zero vector by 0 bar because it is not the usual zero, usual numeral zero. It is the zero vector. So I know that if I take an element from x, from V, and if I multiply that vector by zero vector, the non-zero vector x doesn't change. And it is true for each x in V. I considered for each velocity, I considered the negative velocity, the inverse velocity. So I'm considering for each element x in V, I'm considering the inverse element y in V, so that x plus y equal to becomes your zero vector, because V plus minus V was actually the net velocity was 0. So if I consider an element x and it is inverse together, and if I add them together, then their addition is actually the zero vector. And try to recall the property 5, which I showed you. For each element x, if I multiply this by some unit element, I am considering that unit element, I'm symbolizing this unit element by 1 bar. This 1 bar, this 1 is not my numeral 1. This 1 bar is any unit element with respect to the set. If it is a set of mass, then we are considering unit mass or blah blah. So in general, I'm denoting this by 1 bar, and I'm writing that 1 bar when multiplied by x, vector x doesn't change at all. And the last three properties which I have written over here, for each pair of elements A, B belonging to F, they are scalars. And for each element x in V, I can multiply them A and B. Now, carefully observe, for this multiplication I have used a different symbol, that is dot. I'm going to explain this to you. So AB into x plus A dot B dot x. And similarly, for in VS7, I have taken two scalars, AB belonging to F, x belonging to V. Then I have added the two scalars, A plus B, and then multiplied by the vector. And then I actually can written it as AX plus BX. And similarly, lastly, I have taken one single scalar and two vectors, x, y, and I can write it as A into x plus y, which is AX plus AY. All these observations, the observations with respect to these physical vectors, have actually helped me to think, to devise a general structure. And when mathematicians actually devise a general structure, they do not consider only single situation. They have considered many situations, and they have seen that this is the basic, this is the mother structure, and all the situations which you knew, they are actually its siblings. Okay, so we are going to study the detailed mathematics of this mother structure and not the separate structures. When you go to the physics, to learn physics, you study the set of vectors and set of masses. Then actually you are studying this. but with a different name in physics. When you go to study the computer, there also you some structures, some topics are there. Maybe that topic is following the structure of vector space. So you are studying that topic with respect to its name, but actually you are studying vector space. Okay, so so that's why I told you that vector space is very abstract and it requires much patience from your end. So if you can study the mother structure properly, you can study any structure. Okay, and therefore sometimes people think that is very abstract, and so they lose interest. But if you once you find interest in this subject matter, then whenever you'll be facing situations, always you'll try to find the inherent mother structure in it. Okay, now let me talk about certain aspects of this definition. For example, why I have chosen this notation plus inside a circle and this dark dot, and what is the difference between these two operations, plus and dot, with respect to the usual plus and usual dot. Whenever I am using this plus inside the circle, then that means I actually mean to tell you that I'm actually considering two vectors. I'm adding two vectors. So to add two vectors, to show you the addition between the two vectors, I have used this addition symbol. But when I'm adding two scalars, I have used the usual addition symbol. So I have used that plus. Actually, the nature of these two pluses are same. They when applied add the things together, but you have to keep in mind that this can only add to this can only add to vectors, and that can only add to scalars. So for example, consider this plus to be some topic, say for example investment. Okay, so two faculties, you can consider me and another faculty from physics department. We are connected to one another with respect to our investments. We are discussing I'm saying this from pedagogical point of view. It is not exactly like that. So with respect to our point of discussion is investments, we are connected to one another. But you are definitely, since you are a student and you are not actually right now studying, so you are not going to get connected to me with respect to this investment. So two students can talk about one particular subject. So this plus is that subject which is actually bonding the two students, and investment is the topic which is bonding the two faculties together. Understood? And when I'm applying dark dot, I mean to say the scalar multiplication. The scalar multiplication is means that when we multiply a scalar by a vector quantity. But here you see, I am not actually multiplying, I am not actually using that dark dot over here. Actually, I'm multiplying two scalars. I'm here inside the bracket, I'm multiplying two scalars actually, first of all. So dark dot has not been used. Once you multiply the two scalars, the outcome, the product outcome is also a scalar. And when I multiply that scalar by the vector, I'm using the dark dot. This is the first point. This is the difference between the pairs plus inside circle and dark dot with usual plus and usual dot. Okay. But once you are familiar with, and once you are sure that what you are doing, you know that I'm adding to vectors, I'm adding to scalars, I'm multiplying a vector by a scalar, I'm multiplying to scalars. As I multiplied the two scalars, I used the usual dot. Once you are familiar with it, once you are accustomed to it, then you may not follow these symbols at all. You simply can write x plus y. The meaning is already implied. Okay. If I ask you that you are adding x and y, is this a vector addition or scalar addition? If you say that, yeah, it is a vector addition, and if you do not use this symbol, then I can agree with you. I may consider this situation. Okay. Second point number 2 is that this property VS3 and VS4, these are extremely important, because in VS3 and VS4, you are supposed to find actually the zero vector, or if I talk about VS4, we are supposed to find the, I mean, the inverse vector. For example, if I talk about the natural number, I'm again going back to the school. If I talk about the natural number is what? Starting from 1 to up to infinity, it doesn't have any zero vector in it. Any zero element in it. Okay, so you cannot actually, you cannot subtract with respect to the natural number set, because if you say that I can subtract, I'll say, what is the result of when you subtract 2 from 2? You cannot reply, because the element is not actually known in the domain of natural number. So identification of zero vector is very important in the vector space, and also the inverse. So for example, if you consider the set of integers, and if I say, give me a number with which when multiplied by 2 gives you 1, you cannot find it in the domain of integer set, because half is not there. So identification of inverse in the vector space is also very important. Okay, point number 3 is that I have written all the rules VS1 to VS8 in a particular pattern. You see this pattern. First of all, I have written the commutativity property, then I have written the associativity property, then I have written the identification of the zero vector, then I have written the identification of the inverse vector, then this unit multiplication is there, multiplying the vector with unit element, then these distributive properties are there. All these things have been written in a particular fashion. So if you think that if I ask you someday that what is the definition of vector space, after reciting this paragraph, you haphazardly choose your properties. You start from VS8, and then you suddenly remember, oh sir, it is VS3. Then you suddenly remember VS5. You have forgotten about VS6. If you do it in a haphazard way, the definition will, there is no point in discussing the definition, because they do not come in a haphazard way. They come according to some kind of fashion, a pattern. For example, if you do not identify the zero vector and you go to look for the inverse element of the elements, then after getting, there is no meaning at all to find the inverse element, because what are you going to do? Because if I say that, yeah, okay, but if I do not know, say for example, I do not have any idea about 0. Okay, I do not have any idea about 0, and I have not searched for something like 0, but I have found 2 and -2. So when I am adding them together, 2 plus -2, then what is that? 2 plus -2 is what? I don't know. What is that? Because I do not have any knowledge about 0. So identification of 0, once you identify the zero vector, then only you can identify the inverse element. So you have to write the definition of vector space as is being shown in this particular note, starting from VS1 to VS8 serially. You shouldn't forget any of these steps. So I recommend you to write the definition again and again and again and again in the copy, so that it gets stuck in your mind. Last point number 4 is that a vector space, you have selected the vector space, a vector, set of vector and a set of scalar. Okay, you are connecting them with these operations. Okay, and the sets of vectors satisfying all these properties, VS1 to VS8, it must satisfy all these properties, and not one less, for it to become a vector space. But if at least one property is violated, at least one means one or more than one. So if at least one property gets violated, the thing is not a vector space. Okay, say for example, if you haphazardly look for, if you haphazardly study the properties, or maybe you have found VS4 and VS5. Okay, you have started with VS4 and VS5, but the set is in such a manner that it is not actually satisfying the VS1 property, commutativity property is not there, then your set is not a vector space. it has to satisfy each one of these 8 properties. If at least one property gets violated, it is not a vector space. Okay, so this is the definition of vector space. Now I'm going to do some board work, and for this I recommend you to write this these examples. I'm going to upload the note which I'm showing, which I'm presenting right now to you in the Google Classroom by tomorrow. You are going to get the note, and also I'm going to upload one book. You have got a book from our library, college library, but actually for studying vector space, I am actually following this book. If you ask me what book you are following, I am actually following Linear Algebra by Stephen H. Friedberg, Insel and Spence. So I'm going to upload that book on also. Yeah, somebody has written, Aniket has written that they have received 2 books. Then I must one book probably by Kreisek, okay, and another book I don't know. Aniket later will tell you, give me the names of the book. If you have that book, I'll tell you by looking into the contents from which particular chapter you must study the topic of vector space. But if you ask me about my choice of book, then this is the good book by Friedberg, Insel and Spence, Linear Algebra. And if you want to follow this book, then I'm going to upload the book also in the Google Classroom by tomorrow, not today. Okay, you'll get to know. And if I can upload the video, my class, I'm actually recording this particular session is getting recorded. So if I upload this recording into the YouTube, because I have a YouTube channel, then I'm going to share the link with you, okay, later, so that you can revisit my lecture. Now, let's get back to let's get back to my original discussion, which I was presenting to you. It is about, you see, these examples. These are some situations you can see. So I actually ask you, I suggest you write, say for example, this question number 1. Question number 1, you write in your copy, and I'm going to do some kind of board work to show you why is it called vector space. Okay, so what is this question number 1? Question number 1, let me read it let me read it first of all. The question number 1 is having a set M. M is a set of matrices, and it contains all the possible matrices of order M by N. Okay, all the possible matrices of order M by N. Some matrices are rectangular matrix, some matrices are square matrices. And here inside the bracket I have written F. It means that you consider a matrix, okay. Say for example, okay, I'm talking, when I will doing the board work, I'll show you. So you are choosing, this F means you are choosing, the field is F. So you are choosing the elements inside the matrix from the field. If the matrix containing some elements where the element has been chosen from the real set, then it is a real matrix. If you are choosing a matrix whose elements have been chosen from the complex set, then it is a complex matrix. So the matrix, if you put the parenthesis only, it is not a matrix. You have to put inside, you have to put the elements. From where are you going to select the elements? You are going to select the elements from the field. I want to organize, I want to conduct a test. Okay, so I want students. What kind of test I want to conduct? I want to conduct a test with respect where some performances with respect to electrical machines are required. So definitely I will not go to select the students from a commerce stream. I'm going to select the student from electrical engineering stream. So that's how, when I'm actually constructing the matrix, I'm choosing its elements from the field. The following operations have been defined over here. We have selected 2 matrices, capital A and capital B, from this particular set. And C is a number, is a scalar quantity chosen from the field. Then what happens? If I consider the I and jth cell, the ijth cell element of this matrix A is Aij, and ijth cell element of the matrix B is Bij. I am not writing the elements by small letters. Here also I am writing the elements by capital letters only. The added thing is the subscript. Subscript tells you that it is an element. So Aij plus Bij are the elements of the ith and jth cell of the matrices A and B respectively. When I add them together, okay, then it actually gives you the sum of the two matrices. I actually get the element of I and jth cell of the matrix A plus B. Okay, I am taking the matrix element cap Aij from the ijth cell of the matrix A. I am taking the matrix element Bij from the ijth cell of the B matrix. When I am adding them together, I get the element of the ijth cell of the A plus B matrix. Similarly, when I am choosing the element from the ijth cell of capital A from the matrix A, and if I multiply this by a scalar quantity, then this is nothing but the element of the ijth cell of the matrix CA, because you know that when we multiply a matrix by a scalar, all the elements, all the individual elements of the matrix get multiplied by the scalar. So these two operations are actually known to you. That's why I told you that you know a little bit of matrix theory. And since you know the matrix theory, that's why I have chosen this example. Now I'm going to show by some kind of board work that this matrix, this set, is a vector space over the field F. I'm going to show that this, with respect to these operations, my the set of all possible matrices, all matrices of order m by n is a vector. It becomes a vector space and satisfies all the properties defined above. So I'm going to stop this share, and I'm going to share a whiteboard with you where I'm going to perform this mathematics. Okay, so you be prepared with your copy so that you can write it if you want. Okay. Hope you are enjoying. I don't know, but still, since it is in the course curriculum, then you have to study. So have some patience and study just. Okay, that much I can say. So here is your whiteboard. I probably, maybe you people are using mobile phones and laptops and desktops. So give some time, because it takes some time to get for the synchronization in the device. Okay. So let's start. So my matrix, carefully observe, because it requires a tremendous amount of patience. I'm again saying my element, my set was m cross n. It is a set of all possible matrices. Set of all possible matrices. Okay, and matrix element has been chosen from, elements have been chosen from a field F. Okay, and thus we get the set m cross n F. Okay, and the operations which have been defined, with respect to the questions are this: a plus b ij is equal to aij plus bij, and c into capital A ij, this becomes c into capital A ij. These operations are actually meant for each I and j. I represents the row and j represents the column. I am going to show that it is a vector space. So we shall start with not arbitrary property, we shall start with VS1. The VS1 is the commutativity property. Okay, so let us select two matrices A and B from the set. Okay, I cannot until I show all the properties are satisfied, I cannot tell that M cross N F is a vector space. Now it is only a collection. Then A plus B, because commutativity property should be shown with respect to addition, A plus Bij, by definition, it is actually Aij plus Bij. Okay, and this can be written as Bij plus Aij. Why? Because you know that these are matrix elements, these are numbers, so you are adding two numbers, and the addition of numbers are actually what? They are commutative. So I can write it as Bij plus Aij. It is the ijth element of B and ijth element of A. By definition, I can write it as B plus A ij. Carefully observe, by definition, and it is true for all ij, and therefore plus, if I consider this as plus, this operation matrix addition, here plus actually is a special case. It is not just an addition, it is a matrix addition, is commutative. It is commutative. Okay, it is commutative. VS2, just a minute. VS2 is about the property of associativity. I have to check whether the things are associative or not. So let us consider for checking the associativity property, I must consider three elements from the set of vectors. So I am choosing A, B, C from the set of matrices. Okay, then I can consider this A plus B plus C ij. Now you can consider this to be one matrix and B plus C to be another matrix. So by definition of the matrix addition, I can write it as Aij plus Bij plus Cij. I am writing, now let me write it in this way, you will understand. Since A is one matrix and B plus C is another matrix, I can write it as Aij B plus Cij by the definition provided in the question. And now I can break this by the above definition. So I can write it as Aij plus Bij plus Cij. All these elements Aij plus Bij plus Aij, Bij, Cij, these are numbers. So I can associate the two numbers Aij and Bij together. And I can keep Cij separate. And that actually is equal to, I can write it as A plus B Ij plus Cij. And this can be written as A plus B plus C Ij. I'm writing it somewhere else, okay, because there are no space. So I'm writing it here so that you can understand. This can be written as A plus B plus C Ij. Okay, so you see, and it is true for all Ij, and since it is true for all Ij, so therefore I can write it as A plus B plus C is same as A plus B plus C. And now I can say, that I'm writing here, I can say that plus is associative. Plus is associative. So two properties have been considered. From this particular step, I'm putting a star over here because after this step, you are going to write this statement. Plus is associative. Okay. Hope you have written, we have copied the thing. So I am going to the next page. If you have missed something, I'll revisit the pages so that you can copy later. Okay. Next, you see, I'm going to check the property VS3. And VS3 property is important because it actually talks about the searching for the zero vector. And you know, we know that null matrix whose whose elements are zero, null matrix, or we can consider that this to be the zero matrix is also a member of M cross N F. Okay, and we select any matrix A from M cross N F, null matrix. Let us denote this null matrix by 0 bar. Okay, and we consider this matrix to be of order M cross N, because otherwise we shall not be able to add the two matrices. Okay, is considered, and we see A plus 0 bar ij by definition can be written as Aij plus 0 bar ij, and that is, you know, it is actually equal to Aij, which is true for all ij, and this implies A plus 0 bar is equal to A, which implies in turn that 0 bar is the additive identity of what? Additive identity of the collection M cross N F. Okay. Now VS4, we choose an element which is actually a matrix. Remember, it is not a number. Capital A from M cross N F, and we know that minus of A ij can be written as -1 into Aij. Why it can be written like this? Because Caij is equal to C into Aij, and this can be written as -1 into Aij, or you can write it as minus Aij. Okay, and consequently we can write it as A plus minus A ij. It can be written as, by definition of vector addition, Aij plus minus A ij. In place of Aij remains same, but in place of minus Aij, you can write now as minus Aij, and that becomes what? 0. 0 bar ij. And it is true for all ij. It is true for all ij, and therefore we can write it as a plus minus a is equal to 0 bar. So we can write that, we can say that 0 bar is the inverse element of 0. Sorry, 0 bar, sorry, just a minute, it's a mistake. We can say that minus a is the inverse element of a. So we have got the additive inverse also. We have got our additive inverse. Next we have to select the property Vs. We have to check the property Vs5. So we can consider a matrix. Let capital A belonging to M cross N, because here the matrix, the set of matrix is the set of vectors, and we consider an element, say, let us write this element by this. It's not actually 1, it is actually a symbol, just this 1 from capital F, and we see that I can write it as 1a ij. It can be written as simply 1a ij, as C is a scalar, C a I j becomes C into a I j. Okay, and this completes the property Vs5. Vs6, what was the property? Try to recall. Let us select two scalars now, two scalar quantities from the set of scalars capital F, and a vector quantity capital A from the set of vectors, that is M cross N F. Okay, now we can write it in this manner: a b c a I j. Try to recall, a b into x is equal to a b x. So I can write it as a b into a I j. This can be written as, now this is your scalar C, I can use this definition. So this can be written as a b a I j. This can be written as a into b a I j, and that can be written as a b a I j. Okay, and this is true for all ij, and therefore a b into a, this becomes a into b a. Done. So Vs6 is satisfied. Vs7 is, let what was that operation? Try to recall. A into x plus y is equal to a plus b into x is equal to ax plus bx. So I have to select two scalars a b from F, and capital A from M cross N F, and then we get a plus b of capital A. This ij can be written as a plus b aij. This can be written as a into aij plus b into aij, and this in turn can be written as a ij plus B A ij. And this is true for, this thing is true for, and I can write, since we know that A plus B ij, let me write it over here, A plus B ij, this is equal to Aij plus Bij. So I can write it as AA plus BA of ij. Okay, and this implies A plus B A is equal to AA plus BA. Here A, B are scalars, capital A is the vector. In place of small x, I have replaced it by capital A. It's a matrix. VS7 is satisfied. Last part is VS8. So let us do it. So VS8 is, what was the property? A into x plus y is equal to ax plus ay. So let us select a scalar A from the field F, and we choose two elements A, B from the set of matrices. Okay, and then we can write it as A into A plus B ij. This can be written as A plus B ij. Why? Because we know that CA ij is equal to CA ij, and also we know that A plus B ij is equal to Aij plus Bij, and therefore I can write it as Aij plus Bij, and we can multiply them in the following manner. Okay, and this can be written as AA plus AB ij. So this implies A into A plus B, A into x plus y is equal to AX plus AY. M into A into x plus y equal to AX plus AY. M into V1 plus V2 as MV1 plus MV2. Whatever you say. Whatever you say. Okay. Therefore, we see that all the properties VS1 to VS8 are satisfied. Okay, and so we can conclude that M cross NF is a vector space over the field F. So you have got another example. You have got another example of vector space, apart from your physical vectors of velocities and masses, which is a vector space. So see, this particular problem, I started from here. This was the starting point. This is the solution starting point. Starting from here, I have proved all the properties VS1, VS2, and then I gradually went to show that VS3, VS4, and VS5, VS6, VS7, all these properties, VS8, all these properties actually I have checked carefully to ultimately declare that M cross NF is a vector space. Okay, so you are going to get, just a minute, Can this particular note be saved? I don't know. Can we save this note? If this note can be saved, its board work can be saved, then I can also send you the board work. I don't know how to save it. Anyways, so oh, just a minute, just a minute. Probably I know. Yeah. So I have saved the board work also. And so what you are going to get is that what I've shown here, that apart from the physical vectors, there is also a kind of set which is also which is a vector space. I am now going to stop this share and let's go back. Let's move back to my original PDF file which I was sharing. So when you are going to get my note in the Google Classroom, then you see that there are other examples also. Question number 2, carefully read this example. Question number 3 is about sequence. Okay, question number 4 is about function. Okay, this example function, this is familiar example. You have dealt with function also. Okay, so this is not new to you. So I have done the problem of matrix. I showed the set of all matrices is vector space. You will show that the set of, let me read the question for you. S be a non-empty set, capital F be any field, and we define, this is just a symbol. You can use any other symbol. It is a symbol I have used. This, you can consider this to be a script F. Script F SF denote the set of all functions from S to F. Two functions f and g belonging to this collection are equal if fs equal to gs for all s belonging to the set S. The following operations are defined for the functions. F plus g of s can be written as fs plus gs. Cfs is written as c into fs. For each s, we are supposed to show that this collection of function is a vector space. You can try this particular problem. Then you can try this problem. After that, you are familiar with, I think you are familiar with this polynomial. Polynomials you know very well. You have done binomial theorem. You have done quadratic equation, relation between roots and coefficients. So you know what polynomial is. So I have defined it properly over here. So you can check that whether set of all polynomials is also a kind of vector space with some operations. Then you can try with question number 2. Question number 2 is, this item is new to you. It's not actually new. You have done coordinate geometry. It is the generalized version of the coordinate geometry. And sequence, I think, is a new topic to you. So, but you can, the operations, the sets are defined, the operations are defined. You can try all these examples by yourself. But if you do not try, then I have nothing to say. That means I cannot pressurize an adult student that he must study and you have to do problems. You are all adults. It is up to you whether you want to solve the problems by yourself or not. It is totally depends on you. I can only suggest. Okay, and I can, if you want, I'm always there to guide you. So I don't know, I'm actually pretty much amazed. I don't know. I told you in the beginning of the class that I am actually using the trial version of the Zoom, but suddenly the class has not got disconnected, and this is the continuously I'm taking from 9:30. There was no disconnection. I don't know why this happened. I'm thankful to God that this happened. So see, it's already 10:58 in my laptop is showing the time, and I have to go to college now because I'm taking the class from the college. Is not I'm actually not getting facility. Your thinking process, okay, change that. Always try to think that you are dealing with a general system. Okay, try to use your knowledge. Try to develop the what should I say, the, somebody is writing our queries. Okay, you have queries now. So okay, I'm going to reply to that. Sorry, I am going to reply. You write your queries, you write in the chat box. Otherwise there will be too much noise. What your queries? VS5. Okay, VS5 once more. Okay, VS5 once more, VS5 once more. From the definition or from the example? F has any range? What do you mean by range? From the example. Okay, okay. Sorry, one by one after another. So let's go back to the whiteboard. Can I find the whiteboard? I don't know. Yeah, it's there. See, VS5 is there. I have selected a matrix from this particular collection, and we consider an element 1 belonging to F. 1 is a scalar. So suppose your F is, suppose I'm writing here, you'll understand. Suppose you are taking a matrix capital A, and your matrix elements are like this: 0i, I0. What is this matrix? This matrix is not a real matrix. It is not a real matrix. It is a complex matrix because all the elements have been all the elements of the matrix have been chosen from the set of complex numbers. Okay, elements have been chosen from the set of complex numbers. Okay, and I am taking the order of the of this matrix as 2 by 2. Now I can consider a complex number. Complex number is your field here. Complex number is your field here. Okay, so I am selecting a number, say I, from this complex number, from this field. Actually, I can select I from this complex number, and when I multiply I by the matrix, what do I get? I get this. Okay, so this operation is what? It is actually a different matrix. Matrix is actually IA. So what operations I have performed over here? I have performed this operation over here. Okay, so the matrix element, if you consider this cell, I can consider this to be my, I can consider this element to be my A12 element. So in the matrix, what is A12 element? I have to get A12 element. Say for I am writing in this manner, CA12. The 12 element of the matrix CA is nothing but when we multiply C by the element 12 of A. Okay, so that has been written. Now in place of C, if you consider a unit A1, suppose in place of C, I have taken here I. So if you consider 1 is a real number. If you are considering real matrix, then 1 will get multiplied by each and every element. And therefore I have written 1. This is just a symbol. This stands for a symbol. Okay, this symbol, I actually understand that you are not familiar with this symbol. You can take this symbol as your one unit element, or you can use this symbol as your unit element. So when 1 is, I'm talking about real number, and this is scalar, this 1 becomes your usual one. Okay, this 1 becomes your usual one. So it depends upon the set, the field. When I'm talking about the complex number, then this 1 becomes your 1 plus I0. Okay, so this is just a notation. So in place of C, I am assuming the scalar 1. When I'm writing it as here, therefore I have written 1 into Aij is equal to 1 Aij. Second question, someone has written F has any range. So Avinash, F has any range. I don't know what you mean by that. F is a set containing scalar quantities. with our initial example, F was the set of masses, and you considered all possible masses, so it was an infinite set. In the mathematical example, no, not from minus a to b. For mathematical example, I considered the set of real numbers. So real number is an infinite set. So here only I have considered the set, the field F, to be infinite set. So its range is actually infinite. There are some examples where you can consider the field to be a finite set, but I'm not going to discuss because it is beyond the scope of our discussion, of our syllabus actually. So here I have considered the set from the field from, the range of the field. I tell according to your statement, it's only an infinite set. So its range is infinity. Real number is an infinite set starting from minus a to, if you say minus a to b, no, it's not minus a to b, you write minus infinity to plus infinity. Any other queries, or otherwise I am going to end my today's session. And if you solve the problems, queries will come only then. I'm going to upload the book later. I'm going to upload the note later, and from the book you solve the problem which I have told you, and also you'll try to solve the problems from the book. Gradually you'll understand what is happening. But keep in mind that you are actually dealing with not a special case, but a general algebraic structure. You are doing your mathematics from a general algebraic structure. I started solving the problem and it took me 10 minutes to solve it because I was teaching you. But in the examination, you cannot take this amount of time. You have to do it quickly. So you have to practice a lot. This is just a suggestion. Okay. So this much for today. I'm going to end my today's session and hope to see you soon. My next class is on Monday, and I will accordingly give you the link. The link is same. Still, I'll give you the link through CR. So bye for now. Hope you have understood.